let's move to our next speaker, Professor Marco Liscidini from University of Pavia, talking about parametric fluorescence in linearly uncoupled resonators. Professor Liscidini, the stage is yours.
Excellent. Can you hear me? Okay, so thanks a lot, Karina, for the introduction, and thanks a lot, the committee, for the kind invitation. It's a pleasure to be here. I've already been in a past version. It's always a great pleasure to attend the BQIT. So today we're going to talk about this parametric fluorescence. So we have been hearing about single photon emission. So in this particular case, we deal with photon pair emission, and with a parametric process, a nonlinear process, which is, in this particular talk, spontaneous four-way mixing, although what I'm going to tell you can be applied also to spontaneous parametric down conversion and other parametric processes. So for the people that are not familiar with spontaneous four-way mixing, you can picture it as the elastic scattering between two photons, and this ends up with the generation of other two photons, and these photons may be entangled or not, but they are emitted in pair. Now, one of the problems of this process certainly is the efficiency. As you can see from these numbers, if we consider a bulk system, the efficiency is very, very low. And but this change if you consider microstructure made out of silicon or other nonlinear materials. And more than a decade ago, we demonstrated that we can have a boost of several orders of magnitude with respect to bulk. Now, among all the microstructure or nanostructure you can imagine, probably the best one and the most studied one to enhance nonlinear optics is a microring resonator, a single microring resonator. We have seen harmonic generation in microring resonator, optical parametric oscillation, frequency conversion, and of course, the generation of non-classical light. And all the papers written here, and I could have provided other dozens of other papers, made use mainly of one single resonator. And there is a good reason for which they did that, because just with a single ring resonator, you have at least three interesting features you can exploit. First of all, a single micro-ring resonator is very efficient. You can have nowadays finesse exceeding 1,000. So this means a huge field enhancement. And since nonlinear process efficiency is proportional to a certain power of the electric field, you can imagine that this kind of enhancement translates then in an enhancement of the phenomena that can be up to 10, 12 orders of magnitude. This is a huge enhancement. Another important feature of a micro-ring resonator is that it's convenient in the sense that there is a comb of resonance which span hundreds of nanometers. In the previous talk, that was a problem. In this talk, this is an advantage because we want to work combining several frequencies. And this is also particularly convenient for second order processes because you have usually resonances for the fundamental and the second harmonic field. Finally, and this is certainly an important point for using micro-ring resonator, they can fabricate it pretty much in any platform that you can name. Here I just listed a few of them, but for example, I could have put also aluminum nitride, silicon carbide, and so on. And people became extremely good in fabricating the high quality factor micro-ring resonator. Nevertheless, in order to perform nonlinear optics in a micro-ring resonator, there are some challenges. In particular, as you can see here, in general, when you have your comb of resonances, these have not the position you would like to have. For example, in some cases, you would like to be equally spaced to preserve a momentum and energy. And this can be done, of course, but I have to work in dispersion engineering and change the mode dispersion of the channel waveguide I use. And this can be done, but it's not always easy. It depends a lot on the kind of system you have, but also if you have a certain process, a certain nonlinear process with a certain coherence length, this becomes very demanding for high-Q system because your coherence length must be much larger than the length traveled by the pulse inside the ring resonator. And this can be very large if you consider high-Q systems. So this is an issue which makes things a little bit more challenging. Another important point is that even if you fix and you find and you engineer your resonance position, the position of resonances can be power dependent. In particular, if you are considering very high pump power circulating in the ring, for example, for OPO. And this is because there are phenomena such as self-phase and cross-phase modulation. And in particular, in this case, self and cross-phase modulation determine an uneven shift of these resonances. Okay, so they change effectively the dual velocity in a certain way. There are also other effects such as TPA, which change also the quality factor of your system. Now, for what concern self and cross-phase modulation, you can again work on dispersion engineering, but this, of course, complicates even more your design. And finally, even if you manage to put all your resonances where you want, sometimes you don't really want the entire comb. And sometimes you have more resonance than you need. And this can be a problem for some particular processes that you can use to generate non-classical light, such as, for example, dual pump spontaneous forward mixing. In this case, what you want to do is to generate light in the central frequency, for example, to generate single mode squeezed light. But the problem is that the presence of other resonances allows also other processes, other nonlinear processes, namely single pump spontaneous forward mixing, which pollute your signal that you're generating. And so, at the end of the day, what you want to do is to manage to get rid of those resonances. Again, all the idea is moving the resonances and the field enhancement where you want. So dispersion engineer has a limited flexibility in this respect. And so we ask, what are the other options? So one possible option is starting again with a single ring resonator, and then adding other resonators which share some resonant frequencies. And you can use these resonators to split resonances and pretty much engineer the position of the resonances where you want. Okay? So this, in this case, you are exploiting linearly coupled resonators, and you use what is known as a photonic molecule approach. So you build up your set of resonances as you would do for a molecule for electronic states. Now, this strategy is pretty good. It works very well, and it has been used for about a decade. So you can see here, this has been done. For example, you can even create a band of resonances in crows. You can apply these linearly coupled resonators to photonic crystal cavities, or you can use ring resonators. And there is a lot of work done by Milos Popovic in this direction, who did a marvelous work with linearly coupled resonators. And here, more recently, just published, we demonstrate in collaboration with Xanadu the generation of squeeze light in an unphotonic molecule. But today, we're going to talk about a different, an alternative approach. And to do that, we start with a resonator, because it works very well, with a comb of resonances. And we put another resonators, very similar to a photonic molecule. But now, instead of exploiting what we would call a coupler, we decide to design an uncoupler. What does it mean? It means that light that belongs to a resonators is redirected in the same resonator for resonator number 1 and the same resonator number 2. And mathematically, this happens when the modes belonging to each resonator are linearly orthogonal. I point out, I stress that this happens also when the resonant frequencies are the same. Okay, so we have no possibility to couple, to have splitting here. Now, when you have these, you realize this condition, you can design the comb very freely. You can put the resonances of the two combs relatively each other as you want. And in particular, if you have also the possibility to use a tuner, you can even, after post-processing, you can even determine the relative position of resonances. This is very convenient because we will see later on that this flexibility have important advantages in nonlinear optics. Now, obviously, if you want to realize two linearly uncoupled resonators, there is a very simple way to do that. You can put one resonator on the moon, the other resonator on Earth, and of course, they will be linearly uncoupled. But this is not a very clever idea because you cannot do nonlinear optics with that. So a few years ago, we demonstrated that there is at least one way to linearly uncouple resonators and yet being able to exploit them to do nonlinear optics. So for example, this directional uncoupler here can be designed using two parallel waveguides, and of course you would choose the proper length And you can see from here that linearly speaking, the two modes are orthogonal. And yet, if you perform a nonlinear integral in a four-way mixing fashion of these of fields belonging to different resonators, this is non-vanishing, which means that the resonators are in fact nonlinearly uncoupled, or at least can be nonlinearly uncoupled. Now, let's try to understand what are the consequences of this. So there are pros and cons, of course. Let's start with the bad news, which is the bad news is kind of expected. So you have a strength of the nonlinearity, which is reduced. And this is, of course, because now the nonlinear interaction between these resonators occurs only in the uncoupler region, okay, not everywhere like in a single resonator. And also, when you try to design this kind of uncoupler, you realize that you have to sometimes slightly increase the size of your resonator. Here, for example, to accommodate the directional coupler, which means, of course, leads to a smaller finesse. Now, if you want to quantify this penalty, of course, depends on the design. It's fixed, so it is independent of the quality factor of your resonator, and can be quantified in 1 to orders of magnitude. Depends on the design. Now, this is certainly a significant amount, although we have to say that if we consider the quality factor and the finesse we reach nowadays, it's not such a big deal. Nowadays, for example, we have sub-milliwatt OPO. So compared to initial squeezer, which requires hundreds of milliwatts, this is certainly not a penalty that worries that much. But let's see if we invested well our efficiency, because we have several pros. First of all, this design now is particularly easy and flexible, in the sense that I work now with resonances that I can full control, exploiting this. In particular, I can control their relative spectral position. I can control their quality factor. I can also control independently their coupling between channels, because I can decide to overcouple one resonator, critically couple the other. And this is extremely convenient, for example, in the generation of non-classical light, where you want to enhance the pump, but typically extract very efficiently the pair you generate. Another important point is that you can very easily compensate for self-phase and cross-phase modulation. And this can be done in 2 ways. One, passively, in the sense that by design, you can design a system such that for any power, the relative position determined by self-phase and cross-phase modulation will be unchanged. And this is very interesting because it means that your device will continue to work in a very broad power range, which is not the case, for example, for conventional OPO. At the same time, of course, if you have a tuner, but you don't need that, but if you have a tuner, even if you start from a system that initially was not designed to operate at a certain power because you didn't realize that, well, you can always retrieve the right resonance position actively. Finally, an important point is that dispersion engineering now is no longer that critical. First of all, because you can think about this system like a system that provides a kind of a tunable effective dispersion. And more importantly, now the coherence length of the process doesn't have to be related to the quality factor, but just to the dimension of the coupler. So even if I work with tremendously high Q factors, I don't need phase matching, in fact, which is a very, very big advantage here. Because sometimes, in order to dispersion engineer and provide phase matching, we give up in other properties, for example, effective area, propagation loss, and so on and so on. So we have seen some ideas, some theory. Let's see if we can make it work. So these are the first example I provide you is our result in collaboration with Xanadu Quantum Technologies. So as soon as we came up with this idea, we wanted to prove that we could linearly couple linearly uncoupled resonator. Okay. So, and we decided to work with stimulated forward mixing in a silicon nitride chip. So we pump the upper ring and we see the lower ring and we generate idle. So first we verify that these resonators were indeed linearly uncoupled through linear characterization. And then we verified that they were non-linearly coupled because we could indeed generate idle exiting the second resonator. And also, we managed to prove that we could change and find a sweet spot of efficiency by tuning one ring with respect to the other and changing the relative position or effective dispersion of the ring. The second example I want to mention is a collaboration with the CL80. In this case, we are talking about spontaneous flow and mixing in SOI, silicon uninsulator. So this is silicon, not silicon nitride anymore. So the idea here was to basically implement the original idea of the reference before, where initially this system was proposed indeed to perform dual pump spontaneous flow mixing. So we want to generate photon pairs in the central resonance belonging to one resonator by pumping in a dual pump configuration the other two. And we want to get rid of the single pump phenomena, which now are highly suppressed because there is no resonance for one of the full photon to be generated. And so we measured the coincidence rate. And in red, you can see the dual pump coincidence rate. And in blue and black, you can see the single pump phenomena coincidence rate, which basically are basically irrelevant in the sense that they are limited by our sensitivity. We have essentially a signal-to-noise ratio of about 1,000, okay, which is by far the largest signal-to-noise ratio ever shown in dual pump spontaneous flow mixing. And if you want to know more about this work, there is a paper coming out soon, and there is a talk at Clio next in a couple of weeks that will be given by our PhD student, Federico Sabato. Very well, so time is almost up, so let me give you some perspectives. So what we want to do next. So first of all, I give you an example in which we realize this linearly uncoupled resonator with a directional coupler, but this is not the only possibility. You can imagine new uncouplers, okay? And for example, this is a collaboration still we have with CL80. This is the layout of the sample we realized with them. And here now the uncoupler is a Mach-Zehnder interferometer. So we can even we realize a tunable uncoupler. And this structure is currently under investigation. We have really terrific performances to show, but not today. And then another interesting thing we want to do with these linearly uncoupled resonators is moving also to second order nonlinear interaction. This is a collaboration with Wolfram Pernis and Münster. And this is the sample that we design, and they fabricate the sample. They already done a linear characterization. More work has to be done here, although you can see already that very easily they got doubly resonant configuration. And if you want to hear more about this, Luca Zappi will present at Clio next in a couple of weeks again talk. So let me finish by acknowledging all the people, and especially my colleagues in Pavia, with a special thanks to Federico Sabattoli and Luca Zappi, who worked very hard for the experiments and the theory I worked and I presented to you. People like Xanadu, people at CL80, in particular Corrado Sciancalepore, John Saip at the University of Toronto. And with this, let me finish, and I want to thank you for your attention. I cannot hear anything. I don't know if this is a problem. Okay, now I think. Yeah.
Can you hear me? Okay.
Yes.
We do have already a question from University of Trento, so from Massimo Borghi and Stefano Signorini.
Mm-hmm.
What is the acceptable level of crosstalk between the two resonators in the uncoupled region? In case the coupling region does not behave as perfectly at density operation, I am expecting to see resonance splitting. How this will impact the purity of photons emitted by a single source, and how do you expect to tune the degree of indistinguishability among different sources? Okay,
thanks for the question. This is a good question. So first of all, in fact, it's actually very easy to uncouple resonators, because if we work with resonances which are sufficiently far, they are already orthogonal because they belong to different resonances. So they have different resonant frequencies. So in general, it's way more difficult to couple the resonators than uncouple them. Okay. But of course, if the distance between the resonances is not particularly large, then you need really to work very hard on the coupler. So, for example, the directional coupler I showed you before, the Mach-Zehnder interferometer I showed you before, for example, has an advantage because in this way the bandwidth is huge. We can see that the two resonators are uncoupled over a bandwidth that is 100 nanometer and more. But in general, let's say that since you work with resonances that are different in frequency, it's not that difficult to linearly uncouple them.
Okay, thank you very much, Professor Liscidini. I cannot see more questions coming up in the Q&A chat on your right, but if you do have them, please ask them as soon as you can. That was really interesting to see your recent work with Xanadu, CLSG, and Münster, and I'm really looking forward to hear more from your experiments. So really thank you very much for your talk.